In this chapter, we are going to learn about frequency modulation. What is FM modulation? FM is a modulation technique in which the frequency of a carrier is very directly proportional to the amplitude of the modulating signal. The amplitude of the carrier is kept constant while its frequency changes at the rate equal to the frequency of the modulating signal. We can see that from the figure, low frequency of the modulating signal and the high frequency of the carrier signal are fed into the FM modulator. When the information and the carrier are fed, the FM modulated signal produced has a constant amplitude, but its frequency has changed. The rate of change of the frequency is proportional to the amplitude of the modulating signal. Here, we try to compare the AM and FM waveform. In FM modulation, the information is conveyed over a carrier wave by varying its instantaneous frequency, while its amplitude remains unchanged. But in amplitude modulation, the amplitude of the carrier is varied, while its frequency remains constant. Let's learn how to sketch the FM waveform. We know that in FM, the carrier frequency changes at a rate equal to the amplitude of the modulating signal. Therefore, we divide the information signal into two sections as shown in figure. Section 1 represents the region where the amplitude of the information varies from minimum to maximum, while section 2 represents the amplitude of the information signal, which varies from the maximum to the minimum amplitude. Based on section 1 and section 2, we can try sketch the changes of the carrier frequency at a rate which is equal to the amplitude of the modulating signal. From this figure, Fmax is referring to the maximum frequency of the carrier when the amplitude of the information at maximum. Fmin is referred to minimum frequency when the amplitude of the information signal at the minimum. Fc is referring to the center frequency. The difference between Fmax and Fmin is called carrier swing. Delta F, or frequency deviation, is the difference between Fmax and Fc, or between Fc and Fmin. Frequency deviation is the maximum change of the instantaneous frequency of the FM signal from the center frequency or from the unmodulated carrier frequency. It is proportional to the amplitude of the modulating signal, Vm. The highest frequency of the FM signal, Fmax, equal to Fc plus delta F. Delta F, which we refer to the frequency deviation. The lowest frequency of the FM signal, Fmin, equal to Fc minus delta F. So, the total change of the FM frequency is called carrier swing. Carrier swing equal to Fmax minus Fmin. From here, we can see that carrier swing equal to 2 delta F. There are 4 important features of FM waveform. Number 1, the frequency of the FM wave varies. Number 2, the amount of the carrier frequency changes is proportional to the amplitude of the modulating or the amplitude of the information signal. Number 3, the amplitude is constant. The amplitude of the FM signal. Number 4, the rate of change of the carrier frequency is the same as the frequency of the modulating or information signal. How to derive the FM signal? Let the instantaneous signal for modulating and carry signal as in equation 1 and 2. In FM, carry frequency changes with the change of the amplitude of the modulating signal. So, the angular frequency and the instantaneous frequency of the FM wave are given as in equation 3 and 4. From here, we can see that the instantaneous frequency of the FM wave is equal to Fc plus frequency deviation cos omega mt. Delta F or frequency deviation is equal to k Vm over 2 pi or delta F equal to kf Vm. Kf is a frequency deviation constant or deviation sensitivity. Kf equal to k over 2 pi. From here, k is a proportional constant. Deviation sensitivity or frequency deviation constant is the amount of frequency change in the carry frequency per unit amplitude change in the message signal. The general equation of the FM is Vfm of t equal to Vc cos theta. The angle of the FM signal, theta equal to integration of omega with respect to time. By substituting equation 3 into 7, theta is equal to omega ct plus kvm over omega m sine omega mt plus phi. By assuming phi equal to 0 and substitute equation 8 into 6, the FM signal Vfm of t equal to Vc cos in bracket omega ct plus kvm over omega m sine omega mt. From equation 9, the coefficient kvm over omega m is also known as modulation index, denoted as MF. By substituting kvm over 2 pi as a delta f or frequency deviation, now modulation index of FM equal to delta f over Fm. MF can have the value of greater than 0 or equal to 0 and less than infinity or equal to infinity. As mentioned before, frequency deviation or delta f represents the maximum change of the instantaneous frequency of the FM signal from the carrier frequency Fc. Frequency deviation also proportional to the amplitude of the modulating signal Vm, and it is independent of the modulating frequency. The maximum frequency for FM wave Fmax equal to carrier frequency Fc plus delta f, while the minimum frequency for FM wave Fmin equal to Fc minus delta f. The total change of the frequency from minimum to maximum frequency is called carrier swing. Carrier swing FCS equal to Fmax minus Fmin. It is equal to 2 delta f. Let's try example 1. Determine the frequency deviation delta f and the modulation index NF for an FM modulator with a deviation sensitive KF of 5 kHz per volt, and a modulating signal is given as Vm of t equal to 2 cos 4 k pi of t. We know that delta F equal to KFVN. Therefore, we just substitute the given parameter. To get the value of modulation index, we simply divide the delta F by the FM. And then we get the answer. It's quite simple, right? Let's try example 2. FM broadcast station is allowed to have a frequency deviation of 75 kHz. If a 4 kHz audio signal causes a full deviation, calculate the modulation index. Modulation index is equal to delta F divided by FM. So, therefore, we just substitute all the given parameters. The answer is 18.75. FM frequency spectrum. FM has infinite number of frequency spectrum. This is because in a frequency of phase modulator, a single frequency modulating signal will produce an infinite number of pairs of side frequency. Therefore, it has an infinite bandwidth. However, most of the side frequencies are very small in amplitude. Therefore, it can be ignored. As obtained in equation 10, the FM modulated signal is given as Vfm of t equal to Vc cos omega ct plus Mf sin omega mt. This equation can be expanded further by using the trigonometric identity. Now Vfm equal to Vc in bracket cos omega ct cos Mf sin omega mt minus sin omega ct sin Mf sin omega mt. The term cos Mf sin omega mt and sin Mf sin omega mt can be expanded further as a trigonometric Fourier series. By using Bessel functions of the first kind of nth order, the Fm mathematical expression becomes as in equation 15. From this equation, the Fm waveform has a component at the carrier frequency and unlimited series of frequency above and below the carrier frequency. From equation 15, J0 is the amplitude of the carrier. J1 is the first set of side frequencies displaced from the carrier by omega m. J2 is the second set of side frequency displaced from the carrier by 2 omega m. J3 is the third set of side frequency displaced from the carrier by 3 omega m. J4 is the fourth set of side frequency displaced from the carrier by the 4 omega m. Therefore, we can conclude that Jn is the nth set of side frequencies displaced from the carrier by nth omega m. Okay, this is the Bessel function for several values of modulation index. How to read this table? Okay, let's say we have MF equal to 1. So from here, we can see that number of sideband equal to 3 pairs. So we have J1, J2, and J3. J0 represents the carrier component. From the Bessel function table, when modulation index equal to 0, it produces 0 side frequency. Number 2, the larger the modulation index, the more sets of side frequencies produced. The values shown for Jn are relative to the amplitude of the unmodulated carrier. For example, J2 equal to 0.35. This relative amplitude indicates that the amplitude of the second side frequency is equal to 35% of the unmodulated carrier amplitudes, or 0.35 Vc. From the table also, A side frequency is not considered as significant unless it has an amplitude equal to or greater than 1% of the unmodulated carrier amplitude, or Jn should be greater or equal to 0.01. The relative amplitude for the sideband, which is Jn, is unitless. To get the actual amplitude for the sideband, we must multiply the relative amplitude Jn with the Vc. So the unit is volt. FM signal contains an infinite number of side frequencies, so theoretically the bandwidth which is required to transmit the FM signal is infinite. However, not all the side frequency is significant. This is because it must have an amplitude greater than 1% of the unmodulated carrier amplitude, or the value of Jn should be greater or equal to 0.0. Here we have two methods how to calculate the FM bandwidth. The first method is by using Bessel function table. Based on this method, the bandwidth is equal to 2 times number of pairs of sidebands times audio signal frequency, or equal to 2n FM. The bandwidth of FM signal also can be calculated using Cousin rule. By using this rule, bandwidth is equal to 2 times sum of peak frequency deviation and the highest modulating frequency. This can be shown as in equation 50. However, Cousin rule is accurate under two conditions. The first one, for modulation index MF greater than 4, and when the relative amplitude of the sideband Jn is greater or equal to 2%. Let's have a look at example 3. Number of set of significant side frequency can be determined if we know the modulation index. Since the modulation index MF is given as 1, therefore from the Bessel function table, when MF equal to 1, it produces a carrier component and 3 sets of significant side frequency. In order to determine the actual amplitudes, we just simply multiplying the relative amplitude from the Bessel function table by the amplitude of the carrier component Vc. Based on the given information, the amplitude of the Vc is 10. Therefore, we can multiply the relative amplitude by 10 in order to get the actual amplitude. The frequency for each of the sideband can be determined using equation 15. This frequency spectrum showing the relationship between actual amplitude and their frequency when MF equal to 1. Please try to understand example 4 as well. At the end of this lesson, you should be able to grab all these outcomes. With that, thank you.